Hello again, my dear students. Now this is part number 2 with our lecture dealing with semiconductor junctions, mainly p-n junction. Let me first start with a very quick briefing regarding what we already have learned in our first lecture, or maybe in our first part in this lecture. Okay, so we first make some sort of a very quick flashback regarding the extrinsic semiconductor dealing with an n-type and p-type material, where we have studied that n-type material are those material where the Fermi levels goes toward the conduction band, and p-type material are those material where the Fermi level goes toward the valency band. Then we start to combine these two energy band diagrams. We start to combine the n-type material with the p-type material. Herein, we find that we have to have what's called a reference. Our reference was the E Fermi, because the E Fermi or the Fermi level is the level at which the probability to find an electron is equals to half everywhere. So we start to plot the n-type portion and the p-type portion with respect to the Fermi level, as you can see in the slide. Now, only minority carriers can move. Electrons in the p-type can move here, and holes in the n-type can move there. However, majority carriers are restricted to move. All the electrons in the n-type will not be able to move to the p-type region due to this barrier. Similarly for hole in the p-type will not be able to go to the n-type due to this barrier. We call this barrier the depletion region because there is no possibility to find electron or holes in this region. If you have an electron here, this electron will automatically slide and go to the right hand side. Or if you have a hole here, this will automatically slide and go to the left hand side. That's why it's a depleted region. And if you remember my first part, I have mentioned that this portion of the material or of this portion of the junction is behaved like an insulator. No free carriers is defined in this region. So based on that, we start to plot what's called the electron concentration, the hole concentration, as you can see here. So this is the hole concentration. Here is a p-type region because the holes is greater than the electron. Here is the n-type region because electrons is greater than holes. So as you can see, this is the overall graph, and we make our terminology. We say that the subscript here indicating the region. So whenever you are talking about a P region, so you will say PP and NP. So the sub P here indicates region. Similarly, when you are talking about the N region, we say NN and PN. While the node subscript indicating the thermodynamic equilibrium, please remember, thermodynamic equilibriums occurred when you have a flat Fermi level, when there is no external applied voltage on the device. Here, as you can see, the total electron current and the total hole current is equal to zero, which is the drift diffusion current. Okay, so this is simply what we have already did in the first part of this lecture. Now we are still going toward the thermodynamic equilibrium. But based on lecture number 3, if you remember, my dear student, we say that whenever you have a tilting, you have a potential. However, we don't have here an external potential. So we call this tilting what's called an internal potential. Here, if you study this electrical field or this energy diagram, what we are going actually to do maybe after a few seconds or a few minutes from now, what we are going, this, as you can see, is some sort of a tilting, which is an indication for a potential. If you have an electron here, this electron will slide and go to this direction, to the right side, to the right hand side direction. So as if you have a positive terminal here and you have a negative terminal here. So electron, my dear students, slide toward the positive terminal, and the holes slide toward the negative terminal. So we have some sort of magic potential, or what we call the building potential. This building potential can be calculated. Actually, in our course, due to the very limited time, we are not going to make the step-by-step revision for this calculated voltage. However, you can do it through our lecture script. If you check our lecture script in the e-learning page, you will find the complete step-by-step revision. But by the way, you are not required to do it by yourself. This is just for your demonstration. Of course, I will encourage you to make it, to make sure that you understand the topic. However, if you didn't do it, no worries at all. Even the final formula that we will going to show is not requested to be memorized. It will be given as a part of a formula sheet. So as far as we have a potential, we can calculate this potential. So the calculated potential actually is as following. This V node, or what's called the building potential. This is a very, very important and critical parameter in our PN junction, or what we will call later in our diet. As you can see, this Vn is equals to Kt over Q. Please remember this Kt over Q. I told you before, this Kt over Q is what's called the thermal voltage, which is equals to 25.9 milli-electron volt at room temperature. Of course, it's a temperature dependent parameter. So for the first impression, we can understand that this V node, or this building potential, is a temperature dependent, as you can see. Ln Na and Nd. What is Na and Nd? Simply, Na is the doping of the P region and Nd is the doping of the N region. So these are another two parameters, and then the Ni squared. Flashback to our lectures, maybe lecture number 2, I believe, and where we got an expression, if you remember, for this Ni, which is the intrinsic concentration. Maybe I can rewrite it to you now in my simple whiteboard. So let me first, it's now started. So now V node, which is the building potential, is equals to Kt over Q ln Na and D over Ni squared. So as you can see, of course, V node, or the building potential, depends on temperature. It depends on the type of, or the value of the doping in Na and Nd, and it depends on Ni squared. Now Ni, if you remember, my distance is equals to root Nc and V e power minus Eg over 2 Kt. So Ni is a temperature and a material dependent. If you remember, Nc and Nv and T are temperature dependent, of course, and also Eg and the effective mass hidden in this Nc and Nv are material dependent. If you remember my lecture, I told you that whenever I give you N, I will say you this is Ni for silicon at 300 Kelvin. So Ni is a material and a temperature dependent function. So as a result, this V node can be changed if you change the temperature. This is the first input, or the first parameter. You change the doping level, either in the N side or the P side, or you change the material. If you change the material, the building potential will change. Another important point, that here it's a double temperature function. V node here depends on temperature, and actually depends on Ni, which is depend on temperature. So actually, this is a complicated function in temperature. Maybe one of the very, very sophisticated questions that I can ask you. If I want to ask you a question that I'm 100% sure that you will not be able to solve, that I will tell you that please plot V node as a function in temperature. It's actually very, very difficult, because here you have a temperature dependent, here you have a temperature dependent, and here you have a hidden temperature dependent, if you remember. So it's a very complicated function with respect to the temperature. By the way, maybe you can use here our simulation tool in SALT, where you can investigate more about the temperature dependent on VD or on V node. Of course, I will not going to ask you in the final exam to plot such a very complicated experiment. It's always better to do such a temperature dependent function using some maybe numerical methods, or some simulation tool like MATLAB, for example, in order to plot such a complicated function. So now we already have understand what's meant by the V node, or the building potential, and we can also understand the concept of the V node. So let me now return back to share my screen again, my dear students, and let's also start operating our laser pointer. So this is a V node, or this is the building potential. Now I'm interested in doing the same that we already have done in the previous lecture. what we already have did in the previous lecture. If you remember, my dear students, that whenever we have an energy band diagram, I told you please plot the potential, the electrical field, and the charge. So let's start doing this experiment together. Let's starting using this electrical field, start using this energy band diagram. Let's start to plot the electrical field, the potential of the further potential, the electrical field, and finally the total charge accumulation. So this is our next homework. Okay, so let's start do it. Again, stop my sharing screen and let's concentrate here in my slides. So what about the energy band diagram? So the first, of course, as I usually told you, the first question is a given already. Plot the energy. We already know the energy. Just see your energy band diagram and you can plot the energy. It's very simple like that, something like that. This is your energy band diagram. This is just a copy paste from the one I already plotted in my slide. So I can also re-show it to you here using my PowerPoint presentation. So let's do it again. So again, this is very simply, this is the energy. So whenever I ask you, please plot the energy, what you are going to do is just you are going to copy paste the energy band diagram given. This is some sort of gift in the final exam that you can just copy paste the figure in the question paper, and then you get the mark for this question. So this is the first step. Then the first output is the voltage, and please remember that the voltage is equals to minus 1 over Q times the energy. So very simply, actually, again, I don't need you to memorize that it's negative 1 of Q. What I need you to memorize that the voltage is negatively proportional to the energy. That's all. So what you are going simply to do, my dear student, is that, okay, this is the maximum, this is the minimum, then this is a reverse function. Very simple like that. So I just need to check that I am in the right direction. So let's make our usual test. What you are going to do is as follows. You will say, okay, I have an electron here. What is going to happen to this electron? Very simply, this electron will slide and go to this direction. So that means that we have a positive potential here, and we have a negative potential or a ground here. This is exactly what you have plotted in the voltage. Here, this is a positive voltage, and this is the negative voltage. That's why electron is moving in this direction, as you can see. So you can easily double check your graph using the method. So the next part is to plot the electrical field. The electrical field, my dear students, it's eta, is partial E by partial X. So what I'm going to do, very simple, is to plot the electrical field. So as you can see in the electrical field plot, I can divide this into 3 regions. Here another region, and this is a circle. Why I make this division? Because simply, here you have a constant, and here you have a constant, and in between you have a variation. So in order to have such a curve, you have very easily to divide it into three regions. Whenever you differentiate, whenever you differentiate a constant, the output is 0. So in this portion, the output is 0, and in this portion, the output is 0. Perfect. And then, what about the middle? What about what is happening here? So here, this is somehow a tricky way in order to measure the electrical field. So we have to assume, or let's assume that this point is the origin. This is the origin point. And what we are going to do is that we are going to make a differentiation for this curve. The easiest differentiation is to assume that this is a second order function. Why this is the easiest way? Because whenever you have a second order function, its differentiation is simply a first order, which is a straight line. So the easiest way, whenever you have a curve and you are not sure that what is the order of this curve, just assume that it's a second order curve and then continue solving. Otherwise, if I already stated as a function, then you can differentiate it mathematically, but for any unknown function, you can assume easily that it's a second order curve. So in this way, you have some sort here of a negative slope. As you can see, this is a negative slope. If you plot here a tangential line here, so you have a negative slope. That's why I am plotting here. This is in the negative region, because the electrical field is negative, and then you will have something like that. Very simple like that. So this is the electrical field. It starts to increase till it reaches its maximum, and then it's decreased back. Maybe you can ask me a question, why it looks like that? The answer is very simple, because in the beginning it's 0, in the end it's 0. So this function should increase and then decrease, so that it tends to 0 by the end of the day here, and it starts with a 0. So this is very simple differentiation. Finally, what about the charge? The charge is the accumulation of, what about the charge? The charge is the accumulation. So here rho is equals to partial to eta by partial x, also partial to e, sorry, by partial x squared. So this is the second derivative. Whenever you have a straight line in the electrical field, then the differentiation of the straight line is a constant. So very simple like that. So you will have here a negative charge here and a positive charge here, something like that. Of course, this is negative because this line has a negative slope, and this is positive because this line has a positive slope. Very simple. That's why it's a negative and this. So now we do it from a mathematical perspective, but we have to ask a lot of questions here. First, why this region is negative? Why this region has a negative charge, and why this region has a positive charge? This is the first question. Second question is, in the first part, you told us that in this region, it's a depletion region, it's a depleted region, no charge. But now you told us there is a charge. So there is some sort of confusion between what you said in the first part and what you are saying now. You told us that this region, it's a depleted region, it behaves like an insulated. So from where we have such a charge? This is the second region. The third question is, why the negative charge is smaller and the positive charge is larger? From where we get this impression? So let's start to answer this question one by one. And let's start with the fact that why we have a charge, or from another way, why you said in the first part that there is no free charge, and now you say that we already have a charge. So let's start answer this question. Okay, so let's start to imagine what is happening here in the depletion regime, because this is actually a very critical step in the understanding of the PN junction. Now, I will try to use some annotation. So if you remember, we have we have a P side of the material and we have an N side of the material. And then we combine these two sides together to form this energy band diagram. So basically, this energy band diagram is divided into two regions. What is in the left-hand side is a P-type region, and what is in the right-hand side is an N-type region. Perfect. So, and then what happens? Now, if you are in the p type region, what is your majority carriers? What is your main majority carriers? Okay, this is a very easy question. In the p-type region, my main majority carriers is holes, and my minority carriers is electrons. Okay, so you have a lot of holes. However, the holes you are having here will not stay anymore here. Why? Because from the hole's perspective, the energy of the hole increases by going upward. So if I am a hole and I'm staying in this point, I will automatically drift and going there. And then what is the problem? Then the atom here, which includes this hole, will turn to be what's called a negative ion. Again, please. Basically, any material has number of electrons equals number of positive charge, or what we call protons. If a negative charge moves, the atom will turn to be positively ion. If a negative charge is added, or in other words, a whole move, an atom will be turned to be a negative ion. Let me describe it from the electron perspective, which is somehow easy to be understood. So now this region includes a huge number of electrons because it's n-type. If the electron is staying in this point, whenever the tilting happens, the electron will drift in this direction. Okay, so when the electron will drift in this direction, that means that the atom including this electron will become a positive ion. Again, let's make it by drawing. So now assume that this is your atom, and this atom staying in this location, and this atom has a small electron inside. Now, this electron will not stay in that because there is some sort of drift. So this electron will move in this direction. So try to. So this electron will move and will go, for example, here. Now, what about this atom? This atom now loses one electron. So it turns to be what's called a positive ion. Okay, so it's positive because at this atom, the number of protons now is greater than the number of electrons. We lose one electron, so it's a positive. Why we call it ion? Because it's a static charge. It's not a movable charge. It's an atom, not an electron. Electron is a moving charge. However, atom is a static charge. If you remember my previous lecture, my dear student, I told you that whenever you are calculating rho, where rho is the second derivative of the energy or the first derivative of the electrical field, you are calculating what's called the static charge. So in this case, you have static charge because the electron left the atom and leaving this atom as a positive charge. This is simply what we have. So whenever you are going to plot the charge, you will find this shape where you have a positive ion and a negative ions. Okay, so why do we have this big extended wide region with a low value of a charge, and why we have here large? As you can see, the height here and there is simply a function of NA and ND. So in this example, for example, ND is greater than NA. So as you can see here, the height in the right-hand side, which is the positive side or the N region, is higher than the height in the blue side, as you can see for NA. maybe for another example, you have an XA, NA, and ND are equal, so you will have a symmetric charge. But as we mentioned, we are under a thermodynamic equilibrium. Total current is equal to 0. So that means that the total charge accumulation in the p type should equal to the total charge accumulation in the n type. Very simple. That's why we are using this very, 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 very important equation. So this is simply the total charge. What is the total charge? Is Na times the region where we are talking about. So let me return back to the example. I settle this. Okay, so again, this is the border. This is the n type, and this is the p type, and the red line is the border. We will call, I will use a point, okay. We will call this region XP. What is XP? XP simply is the depletion region in the p side. So if this all is the depletion region, XP is the portion in the p side, and XN is the portion in the n side. So W, which is the total width of the depletion region, is XP plus XN. So now this XP is the region in the P side. So in order to calculate the overall number of holes here, it simply is Na. Again, please remember that Na is concentration per centimeter cube. So Na multiplied by the Q, which is the charge of one unit charge, multiplied by the volume of this portion, which is XPA. XP is the distance and A is the area. And if we would like to calculate the overall total energy or the overall total charge in this region, it's Xn times A times Q times ND. So simply, I'm sorry, let me do it. Okay. Let me do it here for you because this is a very important, my dear student. So here is our energy band diagram. And I told you that, okay, this is the border. Okay, so, and now this is the overall width W. This W is divided into two regions, this one and this one. This is X, this is XP, and this is XN. So what about the total charge here? Simply, it's the unit charge times the amount of a charge per unit volume, which is Na. Again, this Na, my dear students, here is centimeter per minus 3. So in order to turn it into number, you have to multiply by volume. So you will multiply by area multiplied by XP. Area times distance is a volume. So this is the total charge in the P type. And what about here? So Q and D, again, area XN. So this overall total charge should be equal to this overall total charge to be under thermodynamic equilibrium. This is very, very, very important. Of course, Q is the same Q, and A is the same A. So simply, you will find that the very important relation of ND XP, NA times XP equals to ND times XN. Very, very, very important, my dear students. So let's turn back to our slides. So again, let me do this. Okay, this is the equation, and then this is the final answer. XP times Na equals Xn times Nd. Again, we use the subscript node to indicate that we are under a thermodynamic equilibrium. That's why we are using this node notation as a subscript in our XP and Xn. And as I mentioned, XP plus Xn is equals to W. Why this relation is very important? because this is one of our tricks in the final exam. Can we calculate W? Of course, yes. There is a very large equation that can calculate W. These equations, W is equals to 2 epsilon over Q, where epsilon is called the permittivity. I believe you already deal with the permittivity in your physics course. So this mu is equals to mu times mu naught times mu r, or the absolute permittivity or the air permittivity times the relative permittivity. Of course, this will be given. Na plus Nd over Na times Nd times V naught. Already we have a relation for the V naught, if you remember. And of course, this W relation will be given. Perfect. And using this relation, you can extract two relations, xn node and xp node. Again, xn and xp are the region in the answer side and the region in the B side. Okay, where is the trick? The trick simply is here. In the final exam, I will told you, for example, calculate W. Okay, perfect. But of course, here I'm telling you that the revision is not required. This is DNR. The revision is not required, and this will be given in the formula sheet, so you don't need to memorize. So, in the final exam, I told you, please calculate the depletion with W. Perfect. It's a direct substitution question. But I will not give you this equation. But I will give you this one. Then you will raise your hand in the on-campus exam if the exam is on campus, or maybe you will ask me online if it's an online exam, and you will tell me there is a mistake in the final exam. You just gave me X and node, but I need W. I will not answer. Why? Because if you know X and W, if I give you this relation, then you can calculate X and W. Sorry, X and node. If I give you this relation, you can calculate X and node. Perfect. And then, if you use this equation, and knowing that Na and Nd are known, of course, for any p-n junction problem, so from Xn node, you can say that Xp node equals to Xn node times Nd over Na. So you calculate Xp node. And then, if you sum these two together, you will get that. So very simple, very simple. Knowing any of these three parameters, or knowing any of these three equations, you can simply calculate the other two, knowing these two relations, that Xp times Na equals Xn times Nd, which will not be given. You should know it. And Xp node plus Xn node is equals to W. Again, this will not be given, and you should know it. So, very, very important. What I'm going to do in the final exam, in the in-class test, maybe not in the in-class test because this lecture actually is not included in the in-class test, but what I'm going to do in the final exam, for example, is I'm going to give you only one equation out of these three. And I'm sure that you know the other two equations, so you can easily get the other two parameters, knowing these two very simple equations. The only two equations I'm requesting you to know from this part of the lecture is just these two very simple equations. Xp and A equals Xn and D. Xp plus Xn equals to W. That's all. Otherwise, you can use one of these equations that will be given in the formula sheet. So now we have terminated what's called the performance of a semiconductor p-n junction under a thermodynamic equilibrium. Again, the sign of a thermodynamic equilibrium is to have a flat band, to have a flat Fermi level, no external voltage is applied. You only have this built-in magic voltage. But please remember that in thermodynamic equilibrium, the current is zero. You don't have current. So up till now, this is a dummy junction, a dummy device. No current is moving. In the next part, my dear students, in the next week, we are going to investigate what if we apply a potential to this device. What if we lose the condition of a thermodynamic equilibrium and we start to conduct electrical current? What will happen? So this will be the topic for the next part, my dear students. where we are dealing with binding of a p-n junction under different conditions. Thank you very much, my dear students. This is the termination for part number 2, and see you by part number 3 بإذن الله. Thank you very much.